Okay, let's continue with sampling distributions when the distribution of population data is normally distributed, focusing in on the shape, center, and spread of a sampling distribution. If we go to the next slide, here's an example. The length of human pregnancies from conception to birth is normally distributed with a mean of 266 days and a standard deviation of 16 days. Suppose a random sample of 30 pregnancies was measured. What is the mean, the standard deviation, and the shape of the sampling distribution for mean pregnancies based on a sample of 30? Well, the mean of the sampling distribution is equal to the mean of the original population, which is 266 days. The standard deviation of the sampling distribution is the standard deviation of the original population divided by the square root of our sample size. So 16 divided by 30, and we get a z-score, not a z-score, but a standard deviation of 2.92. The shape of the distribution, now we have perhaps a large sample size, but even more so since the original distribution is normally distributed by default, the shape of the sampling distribution will also be normal. So here's another example. Okay, let me expand this out a little bit here. So the heart rate for a typical college student is normally distributed with a mean of 80 days and a standard deviation of 16.5 days. Suppose a random sample of 10 students was measured. What is the mean, the standard deviation, and the shape of the sampling distribution for mean heart rate beats per minute for a typical college student based on a sample of 10? So stop the recording and tell me what, and write down the answers, and then confirm your answers when you press record again, or press play again. Okay, here are the answers. The mean of the means is equal to the mean of the original population, which is 80. The standard deviation of the sampling distribution is the standard deviation of the original population divided by the square root of the sample size, which is 16.5 divided by the square root of 10, which is 5.22. And the shape, what is the shape? Well, sample size, it's small. However, since the original distribution is normal, then the shape of the distribution is also normal. Now, if this heart rates are right skewed, sample size of 10 wouldn't be large enough, perhaps, for this to be to make it enough to where the sampling distribution is bell-shaped. But since it's already bell-shaped, the parent population, then the sampling distribution is also bell-shaped. Here's an example of this. Let's go to the applet here. So if I were to, say for instance, if I only take a sample size of 2, and I did it multiple times, notice here that we have still a bell-shaped distribution. The spread's a little bit smaller than this, but we can also look at, say, we can look at the means here. The means here are about the same. And if we took the standard deviation of the parent population divided by the square root of 2, it should be close to this number right here. Now, if we decide to say, let's take a sample size of 25, and we did it here, and I were to do a sample size of 25 a few times here, now I'll just do it a bunch of times. Notice here that the distribution is also bell-shaped, but notice here that the spread is a lot smaller. The mean of the original population is equal to the mean of the sampling distribution. If we take the standard deviation of 5 from the parent population divided by the square root of 25, notice here it's equal to 1. And that confirms what we discussed earlier. Okay? And the shape of this distribution is bell-shaped. And notice the spread is a lot smaller, which is going along with the standard deviation being smaller than this. Okay? Now to summarize what we have covered for this unit here, the key points are these here on this last slide. The central limit theorem versus the law of large numbers. Central limit theorem is our sample size n increases and becomes large, the sampling distribution becomes approximately normal. Compare that to the law of large numbers is as the sample size n increases, the sample means draw closer to the population mean. So the central limit theorem deals with the shape of the sampling distribution, and the law of large numbers deals with the accuracy of our sample mean being estimating well our population mean. So those are the distinctions. So you should make the distinction between those two. Secondly, when is the distribution of sample means normal? It's one of two ways. It can either be when the parent population is normal and or when the sample size is large. Those are the two ways that our distribution of sample means are normal. And then finally, the mean of the sampling distribution of sample means equals the mean of the parent population. So mu of x bar, or the mean of our sample means, is equal to the true population mean. But the standard deviation of the sampling distribution equals the standard deviation of the parent population divided by the square root of our sample size. So it's the standard deviation of our sample means equal to the standard deviation of our population divided by the square root of n. And that concludes lesson 6.